my talk is very unentertaining, maybe. But hopefully it has some information value in case you haven't followed, the change logs, for example. So I'm going over items in change log just for, some of them are not from change logs, but just trying to kind of give a little bit more details, maybe from things that Tanya already mentioned that are new in the library, starting from the last workshop, and even maybe repeating some things from last workshop, basically the last release plus development since then. So hopefully, yeah, it's informative. It's not very entertaining. Okay, so these are some things that Tanya already mentioned. We had one release since last year, and that happened in April, version 4.8. And this is something also Tanya mentioned, that starting with the current master and any following release, MFEM will require at least C++ 17 to build. And in other words, 4.8 was the last version that the minimum required for which is C++ 11. So we jumped 11 to 17 directly. I think it's been the trend recently for a lot of projects to consider kind of the C++ 17 almost like a bare minimum at this point. Okay, so we are using these features, for example, in DFM, something that I'll mention here. Okay, so we break things down, I guess, meshing additions and improvements. So the first two bullets are related to TMOP. This is our mesh optimization framework using node movement. And so one feature that was added in the time frame that I mentioned was applicability of the algorithms to periodic meshes. So these are topologically periodic meshes, but they actually are viewed as kind of non-periodic mesh. So they required some internal rework, but for users, it should be transparent. So topologically, periodic meshes should be handled now in TMOP as any other mesh. And also there was some metrics in the TMOP definition. So TMOP is based on metrics that measure the quality of the mesh based on various formulas. So some of those formulas were harder than others to differentiate by hand. So right now, and so they didn't have actually derivatives computed manually. So right now they do have those based on our dual numbers, I think mostly, or yeah, but they're now available, should be available for all the TMOP matrix. Okay, so next bullet will be a parallel anisotropic refinement on hexahedral meshes. So this has turned out to be a bit of a challenge, supporting anisotropic refinement in parallel, how to propagate refinements. So we do have this capability in serial, but parallel version somehow is eluding us, bringing up a lot of corner cases. And we kind of work on it from time to time, and it's not really been a push for us, like real need for this capability. So, but it's a kind of cool capability. So we kind of work on it when we have time. And kind of as a middle ground, we have this new version that's you can apply it, but there is like a check that has to happen if things work out well. And in many practical cases, this might be sufficient. So we have it as a capability, maybe as a stepping stone for something that should work in any case if you're interested in kind of extracting the most of refinement strategies. Anisotropic refinements are very powerful. So having those can be a good thing for a code that's striving to do a lot of local feature capturing. Okay, so another small thing related to meshing is the surface interpolation mini app through NURBS. It's kind of cool. Small mini app, you have a set of points. You can then interpolate it to a NURBS mesh, kind of smooth it out. And maybe you can then refine it or do certain things. It's I'll show a screenshot of this in a following slide. Okay, so the next topic are discretization improvements. And the first here is, you already heard, we call it DFAM. And we have kind of alternative spellings here with the delta or with a D, depending on which one you prefer. We kind of like the DFAM because that's the sign of derivative, and I guess that's where D comes from for derivatives. So this is a feature that Julian will describe in more detail, but the one sentence summary is, yeah, this is a new way of writing like bilinear forms or integrators, and that will allow it for users to do it in a simpler way. Hope that's the hope, and also allow you to automatically get derivatives of the if you have like nonlinear forms and things like that for whatever application of AD you may have. And I think Tanya also mentioned this. So this feature is now in the future namespace inside the MFEM namespace. And it's there because, yes, we'll probably need to adopt some of the API to, when the whole capability is more mature and we feel that the interface is stable, we'll move it to basically on the level of MFEM. And yeah, there is one example, that minimal surface example. So we already have a minimal surface example, but I think that one doesn't use AD, and so this one uses AD. It's a slightly different version of minimal surface. And yeah, so the rest you'll hear in Julian's talk. So this is one cool addition to MFEM, and their actually respective paper on this, bounding higher order functions with piecewise linear bounds in 1D or multiple dimensions. So this here, what we mentioned is really bound computation for a given function, but this also works for bounding curved meshes and the Jacobians of the transformations for these curved meshes. So this can be very powerful if you're trying to detect, okay, is my element actually inverted somewhere? It will kind of apply it recursively and zoom in places where the Jacobian becomes small, and it can actually figure out, is it positive or does it actually go negative? Okay, so this is something that I think I mentioned last year as well, but now it's really fully merged into MFEM, the support for pyramids, the whole DRAM complex. And I have at least the two main papers I believe that the implementations are based on. So the first one is, I guess there are two families that you can define, and when that's possible, we have both implementations, I think. And on top of that, we have the positive basis for both H1 continuous and L2 discontinuous spaces. Okay. So in the refinement side of MFEM, we have now support for parallel P and HP refinement for quad-C hexes. Only isotropic refinement, as I mentioned. Anisotropic is a bit more challenging. And there are mini apps that illustrate that, HPref and PHPref in the directory that I've highlighted there. There was a PR that improved on the hyperbolic system support. There was some renaming that happened, but I think the older names are probably still, I think they're still there. That's typically what we try to do, not remove them immediately. Maybe it's deprecated, so you may get a warning for now. Just a reminder to change the name at some point. So small improvements, quality of life. And then in the feature, the submesh feature, which was also new, maybe last year, this last period, we added support for non-conforming meshes, and this was worked by Hugh mostly, I think. And yeah, so you can extract volume and surface submeshes of an existing non-conforming mesh. So not quite straightforward, I guess, as far as I understand it. Okay, so one feature that was added to, I think this was work by Ido and maybe Ido Ackerman from the Netherlands. We've been collaborating with him for a long time on NURBS, on and off. So one of his last contributions was the addition of HCurl and HDiff elements for NURBS-based elements. And for now, this is limited to single patch meshes, but if there is interest, and I think he has interest to maybe develop this further, make it more general. Okay, more discretization improvements. So this is something that can be helpful in some cases when you have the finite element space in the diagram that Sunny showed. Like one of the operators is something we built for you, like the operator that goes from, well, I guess in that diagram it's a little, so it's the operator that goes from what we call a grid function or L vector to the real true degrees of freedom that are unique globally. So this operator is what we call usually prolongation or parallel prolongation in the parallel case, but you can also have it in the serial case when you have non-conforming meshes. So this operator generally will build it for you, but in some cases, you may want to tweak it yourself and give us actually that operator for us to use it, either for the final assembly or just to manipulate the transition between your true degrees of freedom and your grid functions, right? So this is something that now you can do with custom prolongation and restriction operators. Okay, so this is something I worked on briefly. These HDiff for HDiff spaces in the quadrature interpolator class. So for those of you that maybe not very familiar, the quadrature interpolator class is, well, in the diagram again, that trying to show the decomposition of the operator. This is really the operator that allows you to compute things from degrees of freedom to quadrature points. So in terms of the vectors, this is, let's see. So this is like going from E vector to what we can call Q vector. So values at quadrature points, values, derivatives. In this case, we have, for HCurl, we have vector values and also values that are transformed via the Piola transformation in physical space. So there is this difference between values on reference space and in physical space. And in addition, we have the magnitude of in the physical space. Something that we're missing here and can be added later is the divergence, let's say in physical space, but also in reference space, because they are, again, different. And this is a scalar quantity for HDiff. So quadrature interpolator is kind of a building block in that diagram. Okay. And I guess the main goal there is that this class has full support for GPU. So all the operations there are with kernels that are provided to run on GPUs. Okay, so some last bullets here. There are some additions to the hybridization class for handling boundary conditions. So a lot of developments around fine points. You know, I always think, okay, now we have pretty much everything with this we can do with GSLib in MFEM. But then Ketan comes and says, okay, well, here is something we can do. And he does add it to the library, which is very cool. All kind of cool additions. And there is another bullet about that in a little bit, but it's under the GPU specific things. Okay, so there is GSLib-based gather-scatter operator. I'm not quite sure what that actually means. Okay, so maybe can tell us. Okay, how am I doing on time? I have 10 minutes? Yeah. I mean, I don't have many slides, so I feel the time, I guess, with more talking. So GPU computing, it's a big focus for us, of course. So one thing that we did not really do much before support this mode where you can build CUDA codes using Clang. And now that's become a bit important and useful because of the use of Enzyme, for example. So Enzyme is relies on LLVM. So to do CUDA, we want to do CUDA with LLVM, so with Clang. So this is something now we can support building with Clang enabled, CUDA enabled Clang, and there are some bullets here. You need to set this CUDA CXX for do make, or set the CMake CUDA compiler if you're using CMake to be either the Clang++ executable or an MPI wrapper of that. And things mostly should work. There are some additional things. You may need to set up your CUDA directory to point to the right environment, things like that. But that's now supported, and we tried to test it as well. Actually, we did uncover some issue yesterday in the tutorial. It was kind of hidden. It's a specific build. You have to do this build, also build it with a shared build. So it was something we did not test, but now we found out that we have an issue, and I think we have a fix now. So there was some work on de-refinement. This was motivated by some internal need to improve the performance of de-refinement in AMR. And this was work by Andrew mostly, or exclusively, I should say, probably. Yeah, and the change is now transparent as far as I understand it. You just use it as before. When you update your function after de-refinement, now it's going to be using the device if you have a device, right? And the algorithm is kind of a device algorithm, so you may have some benefits even if you're just running on CPU. But it's something that should be transparent to users. And yeah, one caveat is that you may need to convert your mesh to non-conforming, which even if your mesh is conforming, you can still convert it and use it. I believe it's a small caveat. Maybe you're paying with some more memory, but yeah. Okay, and yeah, so this is another big bullet point for fine points GSLib. Now it can run on GPU. And you need to use a newer version of GSLib as indicated here. But yeah, so this very nice library GSLib now, we can use it on GPU as well. So it's a combination, I believe. It's some of the capabilities for running on GPU are maybe there were some updates in GSLib, but I guess mostly things are actually in MFEM, so it's kind of working together between GSLib and MFEM. So it's not like we just borrow what GSLib did. It's building on top of it to support fully the GPU execution. And some other feature that can be useful for various things. Batch linear algebra based on cuBLAS, HIPBLAS, Magma, if you want. And some native, not very performant probably, FM implementation, or maybe it's good enough in many cases, but cuBLAS and HIPBLAS, they just come with your CUDA or HIP development environment. So yeah, that's no need to reinvent the wheel there. Okay, some more GPU computing. So one thing that we introduced, and I don't know if this was actually available last year, I think it's new maybe since then, the capability to define and dispatch GPU kernels in different integrators. So when you have, with this framework now, we can define a template function, and then inside the MFEM library, we can instantiate certain cases that we think are good to have as part of the library. But if you have another case, let's say a combination of certain polynomial degree and certain number of quadrature points, and we don't have that in MFEM, you can instantiate in your application. So this is one thing that it allows you. And that is currently it's supported in these two integrator, diffusion and mass, but I think we've added since then some other classes where this is now possible. And you can actually test if you define these variable MFEM report kernels. If your code runs through a code path and doesn't use an optimized version, it will tell you, and then you can say, okay, I need to instantiate it myself, and I can use that to improve performance. Basically, sometimes the performance can be drastic between the fallback and the optimized version. Something to keep in mind on mostly the performance difference on GPU can be very drastic. On CPU, maybe not so much, but yeah, like using shared memory on GPU makes a huge difference in many cases. And the fallbacks typically don't do that. Okay, so we have so another bullet. This is a batched inverse transform. So this is the class in FM. So actually, this is the non-batched version, is what allows you to say, okay, I have this point in physical space. Well, I want to find which element it belongs to and what is the reference coordinate of that point. So I have the physical coordinate. So I kind of need to invert the transformation mapping from reference to physical space. And we have this version that's purely running on CPU. And now, thanks to Andrew again, we have a GPU implementation that does batches of elements, because GPUs, they need more work. You don't want to call them one element by element. So this is a batch version of this algorithm that is accelerated on GPU. And some final small things for GPU computing. So this low order refined to high order transfer operators, these are things that can be useful if you're coupling your high order code with more traditional, let's say, linear FEM, or maybe it's not even FEM, it's maybe a finite difference, or if it's finite volume. This is kind of a coupling too. You can think of it like that. And there are some examples how you can do these transfer operators, as mentioned here. And yeah, some additions to two of the integrators to support GPUs. So there are some additions for linear, nonlinear solvers, method of moving asymptotes. That's an interesting method widely used, I think, in topology optimization, for example, but also in other optimization problems. So just quickly mention, we added support for Sundial 7. And now we had the class iterative solver monitor, which was meant to allow you to view into how your iterations are going. And now we decided, okay, we now wanted to be able to control actually your iterations by saying, oh, you're done. I've converged based on user-defined criterion. So we call it controller now, but we still keep the old name for backward compatibility. So some examples, I'll just mention here the boxing mini app. So this is some I mentioned for grid functions. And this allows you basically to get a box and an estimate of the Jacobian for every element in your mesh for higher order meshes. And this last is just an example doing that for grid functions. Higher order grid functions, you can bound them. It's an example how to do that. And let's see, I'll skip this. Well, there are some of the movement if classes like namespace tensor and dual, they were moved inside the future namespace. Skip the rest in turn time. So this was an illustration of the NURBS surface interpolation. So you start with this, you interpolate it nicely and smoothly, NURBS, then you can refine it if you want. So I'll skip this. Let's see if they had. So there were some new things in GeoVis. And again, to keep things on time, I'll skip them. Just be aware that, yeah, we've been mostly Jan and Andrew, actually, I think they did some new development in GeoVis, which has been mostly stalled for a few years, maybe. But now we have some new things there as well. And yeah, so these are, mentioning the seminar. We have the online tutorial that actually happened yesterday on AWS, but you can also do it at home. And PyFM, highlighting PyFM as a feature that did not mention, but it's definitely something that becomes more and more important, I think. And that's it. Like that.